Okay, so good afternoon, everyone, and welcome to this session of WIDS Noida. WIDS, Women in Data Science, is a global conference of Stanford that aims to educate and inspire data scientists worldwide. WIDS also has several regional events worldwide and aims to support women in this field. So WIDS Noida is actually one of these regional events. Now, I am Anushka Narula and I will be your host for this session. I am a CSE undergrad at Indira Gandhi, Delhi Technical University for Women. I've always been a strong advocate of inclusive growth and development in all fields. I'm an enthusiast and I love working on different technologies and just grab up different opportunities to succeed in my own. So that was something about me. Now it's time to introduce our speaker. So today we have with us the phenomenal Kashvi Srivastava. Kashvi has recently completed her graduation from Delhi Technical University in Mathematics and Computing Engineering. She has researched on several areas, including the scientific computing, intersection of applied mathematics and artificial intelligence, differential mathematics in physics, physical science, and deep learning. She is also a part of several technical communities and is contributing amazingly. Not just that, she would be joining the University of Michigan as one of the University of Michigan, which is world's premier academic institute, as a PhD student. So welcome, Kashvi. We are so glad to have you here. Over to you.
I'm quickly going to share my screen and then we can talk further.
Okay.
Yeah. Is the presentation visible?
Yes, it is.
Okay. Thank you so much.
Kashvi, you're not audible. So can you just pause for a second and try doing it again?
Okay. Okay. So I was not audible from the very beginning?
No, like when you were introducing, but yeah, from the slide you were not audible.
Okay, no problem. I'll just go through it again. So yeah, as Anushka generously introduced me, I am an incoming PhD student at the University of Michigan. And my program is going to be in applied and interdisciplinary mathematics, which means that I'll be working in two departments simultaneously. One would be mathematics and other, I'm hoping, computer science or physics. Then I've just graduated my Bachelor's of Technology from DTU in Mathematics and Computing Engineering. Again, most of the coursework was in mathematics and with some applications in computer science. Because I'm interested mostly in research, so these are some of the broad areas that I'm most inclined towards. Numerical linear algebra is more or less scientific computing, as Anushka said. It involves a lot of data, it involves a lot of math, and a lot of computation, computational math. Then comes optimization, both derivative free and black box. There is obviously, of course, intersection of applied math and AI that we are going to discuss today. There is differential mathematics, which has most of the applications in physics, as you know, those heat equations and PDEs and everything, and obviously deep learning. So yeah, I am the most active on LinkedIn. You can always ping me there. I have a growing blog wherein I share my experiences, and you can find some tips for applying to places and for tests and everything. And you might find a coming section on math and technology. Other than the work part, I really like reading books. I think I've mostly read psychological thrillers and science fictions. I love dancing. I am a trained classical dancer. And I also like making friends. So you can always ping me on LinkedIn. You can always find me there, and I'll reply to you in in very less time, always, no matter what. So yeah, quickly moving to the content summary. What all are we going to cover today in this session? So I'll briefly introduce what is artificial intelligence, and then we will jump to why do you need to explain AI? Like, why is there a need for explainable AI or interpretable AI? And if your AI, artificial intelligence model, or even data science model is not explainable, then it is known as a black box, right? So we'll see a very interesting example of a black box model. Then obviously the most important question is whether maths is required for explaining AI or not. Do you need math to understand or explain your AI or even data science model? We'll include a case study as to what questions you would need to answer from a mathematical point of view. Then if we have established the why part till then we'll move on to the what part, as in what all math do you need to actually start your journey. And then we'll move on to the how part, as to how to start learning for your data science journey. And in the end, there is a little sneak peek to whether AI can be used in solving math or not. It's the, it's the flip side of the entire topic. So let's begin with what is artificial intelligence. I would say it is the science, in very simple terms, it is the science and engineering of making intelligent machines and intelligent programs. It is used for understanding human intelligence. It is also used for simulating human intelligence or replicating human intelligence, I would say. But according to me, at least, it is not limited to both, right? Like, AI researchers around the world have the freedom to design programs, design machines which do not have properties which are biologically observable, which you have already seen in human intelligence. So they can develop programs, they can develop machines which have more computation than human intelligence or have different features than human intelligence. So it is not limited to both. And if we talk about, the correlation between all of these hot topics that we keep on hearing these days, I found this really cool Venn diagram on Towards Data Science. It has the correlation between these topics. So artificial intelligence is the entirety of it all. Like, it includes everything. As I said, it includes everything that is trying to understand and that is trying to replicate or simulate human intelligence, right? Then there is machine learning, which is a subfield of artificial intelligence. And it includes the algorithms, which basically learn on their own. They keep on learning as they are training. So they develop a sort of intelligence in themselves. And then comes the deep learning, which is another subfield of all these two. And deep learning is basically trying to imitate the functioning of neurons in human brains, that neural network stuff. Because all of you are data science enthusiasts here, if we were to place data science on this Venn diagram, I would say that it is another huge field which is intersecting all three of these, right? So it has some uncommon features such as analysis, such as visualization, which basically comes under data handling, but it has many common features with all three of these. So I would say that it is another huge field which intersects these three. Now, as someone who is designing AI, who is modeling, as you and me, we're modeling AI, right? We are creating AI models. So what is the thing that we're most concerned about? We're most concerned about the target audience of our AI. Where is it that our models are going to be used, that our creation is going to be used? So let us say our models are used in medicine, law, or defense. Then the domain experts, the experts in that particular field, are going to use our models, right? Then comes the users affected by model decisions. Now that AI is pervasive, it is present everywhere. There are many people who are going to be affected by whatever our model is deciding, by whatever results we are obtaining from our models. So there are actual people who are getting affected by that. There are regulatory entities. They're basically some people who verify the legislation part of our models. Then there are data scientists and developers who use this for research and better performance of models and of the whole concept. So the models that are being used right now are mostly black box. You will see in a bit why I'm saying this, but they are. As in the figure, they're just taking an input. The working is entirely a black box. We have no idea how to analytically express the working. We have no idea how to, understand or explain the working to someone. And then we are receiving an output, which is used everywhere. So the question here is, why is there a need to explain our AI? Why do we need explainable AI, right? There are multiple number of reasons. As I said, there are many people who are going to get affected by what your model is deciding. So these many reasons are there, which basically vouch for the fact that your AI model should be explainable. Now, I'm not going to go into detail of all of these reasons. I guess I believe that the terms are self-explanatory in its entirety. You can easily see the term and understand why do we need our AI to be this particular feature of explainable. Because if in the near future we want our AI to perform well without human intervention, if we want our AI to be removed from human intervention totally, then we would want our AI to be compliant with these all terms, right? It should be trustworthy. We should trust our model to perform in a certain way. We should trust our model that it will produce results in that we want. It should comply with causality. Causality means that we should know that a certain variable causes a certain variable to behave in a certain way. So we should know what is causing what in our entire model. It should have transferability. So transferability is something that is actually causing you to apply that testing, training and testing approach in your all of the models, I guess, AI and data science even. So transferability, you want your model to transfer from one data set to another data set. It should be informative. Obviously, it should support decision making in some way, right? It should be informative. We should have confidence in it. We should confidently be able to say that our model is robust, it is stable, it can handle situations, right? Different situations. It should be transparent. Again, like a black box is not transparent, right? We cannot know what is happening inside of it and why we are getting a result if we are getting it, and why we're not getting a result if we are not. So it should be transparent in that way. It should be fair. This one's pretty interesting because I've linked an article to a very interesting model that I came across. I'm not sure if I'll get to share my slides on some platform, then you can easily go to that article and read for yourself. So this was some time back that some researchers tried to develop a model wherein they were trying to predict the percentage of criminal activities that a convicted criminal can commit in the future. So how much more crime can a convicted criminal commit, right? But and this was totally like the entire goal of this model was to remove the human bias, right? We should remove whatever whatever bias prejudices humans have. So this was created for that. But guess what? The model was discovered, the model was learned to be biased against minorities. So we need our models to be fair and they should not be biased, because there are actual human beings on both sides, right? Then it should be accessible. Obviously, if it is going to be used in many and many fields who do not have much knowledge, people who don't have, their backgrounds in AI, they don't have backgrounds in machine learning, they should be able to access the model, they should be able to understand the model, and the working of the model should be interpretable. Interactivity, obviously, it should be able to answer the questions that we have about the working, about the results, about the predictions, and all of that. And of course, it should comply with privacy awareness, right? So these are all the reasons that we need an explainable AI, and we need to actually understand and interpret and explain our AI properly. Now, this is a very interesting example of a black box model. As I said, if your AI, if your model, if your working is not explainable, it is not explainable to people, it is not explainable to even yourself. If you're working on a black box, then there are people who are going to get affected, right? So this paper is particularly interesting because the paper got the Best Paper Award for ICLR 2017. I'm sure you must have heard about that conference, which is very famous in this field. So get this, right? There are images from the ImageNet database, and these are correctly labeled right now. Like dog is labeled dog, flower is labeled flower, and yeah, so we are trying to train a neural network to classify the images according to their classes, according to their labels. Now, the neural network should perfectly converge on this one, right? It should train on the data perfectly, and it should learn the data perfectly, right? But if we were to actually shuffle the data, we were to randomly shuffle the labels of the data, as you can see, I have mentioned that the two almost identical flower images are now labeled dog and bird. So according to our conventional knowledge of AI, according to our conventional knowledge of convergence of neural networks, this should not converge, right? Because obviously the correlation is completely destroyed here. Two identical images are labeled differently. So how does our model converge? Or even if it converges, the convergence rate should slow down, right? By our conventional knowledge, that is what we believe. But it was not the case. The paper actually showed empirical results that the convergence did happen perfectly. The neural network was able to perfectly fit the data, which I was completely surprised. I was completely shocked by this. I read the entire paper and I was not able to make this out. So it clearly poses a question to all of us that whether we understand our model or not. Do we really understand the working? Do we really understand how is it converging, or how is it actually generalizing to other data sets? I don't think we have any idea. I didn't after reading the paper. And I've written the paper if you want to go through it. But yeah, it actually poses a very important question in all the research that has been done till now for regularization or generalization of our models. If you are convinced by now as to why we need to understand our models and why we need to explain our models properly, I know you must have the question of whether maths is required for this or not. Whether is math really required for explaining AI? When we have these many good packages, excellent packages for visualization, for prediction, for classification, regression, we have everything already done in the packages, and we can just use whatever they have developed till now to make our own model. Like we have PyTorch, we have Keras, we have scikit-learn, we have TensorFlow, we have all of this. So why do we need math, right? You must be thinking about this. But at this point, like I am just going to reiterate my whatever I've said till now, because there are black box models that are increasingly used in many different domains. There are people getting affected by the model's decisions. There are actual human beings who are on both sides of the models. We are creating it. If we do not understand what is going into the model, then we are not taking the responsibility to actually pass on the results to some other human being. So the demand for explainability and for interpretability is rapidly increasing. These are both different terms, mind that, and these are often used interchangeably, but the demand for these both are increasing rapidly. And for all of this, the stakeholders of AI are responsible. Now, you would ask, who are the stakeholders of AI? So I just trace back to something the father of AI, John McCarthy, said, that the abilities of computer programs correspond to the intellectual mechanisms that program designers themselves, the intellectual power that the program designers themselves put into the programs. So I think it is clear that it is us who are designing the model, who are creating the models, who are developing AI as a research field. It is us who are responsible for actually creating explainable AI. And is math required for it? I'll just present a very simple case study. I think the framework is for a machine learning model, but it is equally applicable to a data science model too. I know machine learning framework is starts with problem framing. It goes to data analysis, data cleaning, and all of that, pre-processing. Then it goes to model building, and finally application. Right? What all questions do we need to answer, which require a sound mathematical judgment, which require you to answer the questions with a mathematical perspective? So what do you want your model to predict? Is it classification? Is it regression? Do you want probabilities? Do you want percentages? How do you answer this without math, I would say? Then how big is your data set? Now, the bigger your data set is, the higher the dimension of the problem becomes. So you need to understand whether you need to handle your data through tensors, through vectors, matrices, and all of that. So how big is your data set is basically the entire question, right? What are your independent and dependent variables, and how do you want them to correlate? So if you answer this question vaguely, then you will not be able to come to a proper concrete answer. You need to answer this question very mathematically. I would say that two variables should be correlated. I want this variable to completely depend on this variable with a correlation of greater than 0.5 and stuff like that. Does your data set require PCA? So PCA is something, it's called principal component analysis. It is something that is used for dimensionality reduction. It is used for feature selection. So it requires a lot of linear algebra, a lot of multivariable calculus. And from the correlation itself, you would want to answer this question of whether a certain variable is actually playing a role in getting the answer that you want or not. If not, then you might get rid of the redundant features. You might get rid of the unwanted features that are just increasing the dimension of the problem. Do you use regularization techniques? Now, generalization is a very important topic in AI. You want your model to generalize better, to work on a data set, to train from the data set, but generalize better on another data set. So do you use external regularization techniques? Are you satisfied with whatever implicit regularization techniques are used in the model or not? External might be a weight decay or data augmentation, wherein you need to change the tensors, you need to augment the tensors, or it might be something like early stopping and all of that. So this all requires your mathematical judgment, right? So what the next question might be, what are the hyperparameters? Now, this is I guess very important question, because from this you try to optimize your results. You try to get the results that you really want by fine-tuning the hyperparameters. So what are hyperparameters? If I say in the terms of a neural network model, you would say the number of layers, or the number of neurons, or the I would say the activation functions and all of that. So all these are hyperparameters, and all this require your mathematical perspective to work through. Then again, is percentage of accuracy a reliable measure? This is the final question. I have missed many questions, but this is just to give an overview of where exactly in your model you need your math judgment to follow. So is percentage of accuracy a reliable measure to judge your model's performance? Is the percentage of accuracy something that you should use in judging your model's performance in comparison to other models? Or do you want to use other measures like F1 score or like precision or recall and stuff like that? So yeah, if by now we have developed why math is required, and if I have convinced you in some way, so we will quickly move through what all math is required. I'm sure you must have heard of all these terms time and again in all those articles wherein you need to learn math before data science and all of that. But I am going to give a very brief, topic-wise introduction to what the subject actually entails and where it is going to be used exactly in your model. So linear algebra, your data is basically a matrix, right? You're handling your data in terms of vectors, matrices, tensors. So you would need linear algebra for data pre-processing, as in the engineering that you do before putting it as an input into the model, and model evaluation. So you would need vectors, matrices, products, determinant, inverse, eigenvalues, and eigenvectors. Decompositions include singular value decomposition, QR decomposition, LU decomposition. All of these are quite important. Orthogonality. Then there comes multivariable calculus. So the higher the dimension of your problem is, the more multivariable calculus you would need. So if you've seen the back propagation step in a neural network, you would know what I'm talking about, because every layer, you need to calculate the partial derivatives of the hyperparameters in every layer. So this becomes a long chain of partial derivatives, right? So you need it for back propagation and for feature selection even. As I said, it is used in PCA. So you would need to know derivatives. You would need to know multivariable functions, which are, I would say, which are used for partial derivatives again. You would need to know gradients and Hessians, which are vectors and matrices of different orders of partial derivatives. You would need to use special activation functions, all those functions that you hear about, the sigmoid function, the hyperbolic function, these all come under multivariable. And you need to know what is function plotting. How do you plot your function? So for this, I might think that I'll require convexity, concavity. I will require how to plot the critical points, what are the derivatives at those points, and whether my slope should go higher or lower, and all of that stuff, right? Now, the next one is optimization. Obviously, you are trying to optimize, you are trying to minimize the error between your model and the actual result, right? You are just trying to minimize the error and trying to bring more your model closer and closer to the actual results. So optimization is everywhere in machine learning and AI. You need it for hyperparameter tuning and modeling, obviously. You will need to know what is the objective function, what are you trying to optimize, what is the error function, what do you need to minimize, and what is the gradient descent algorithm and its variance, like stochastic gradient descent and all of that. Other than that, there comes probability and statistics. I think this is the most, the hyped up math that is required for machine learning for AI. I'm sure you must have seen the one meme wherein there is a mask over something and the mask says machine learning, and then you remove the mask and it's just statistics. But that is what I believe, actually. It is just statistics with a mask on. So it is used for the entire model engineering, and it is used for predictive analysis. You will need to know descriptive statistics, which I would say is a fancy term for the mean, median, and mode that you study. You will need to know correlation, as I said, between two variables. You would want to know what is causing what. You will need to know covariance again. Probability distributions, all your normal distribution, Gaussian distribution, uniform distribution, and all of that. Bayes theorem, conditional probability. And then hypothesis testing, obviously. You would want to start with a hypothesis of how your model should perform, right? So I will quickly go through some of the resources which should help you in starting your math journey. These resources are all tried and tested. Like, I have gone through most of them, and I have loved these for my mathematics courses. And I have added the links. If you get a hand on the slides, then you should definitely go and check them out. The first one is Mathematics for Machine Learning Specialization by Coursera. So this one's pretty good. I think there are 3 courses in this one. There is linear algebra, there is multivariable calculus, and there's PCA. This one's a good course if you're trying to start with the introductory part, and you're trying to generate your curiosity for learning more. It is very brief and succinct. Another online course is Essential Math for Machine Learning, Python Edition by edX. Again, the same jargon. You would want to learn more. This is very brief because obviously it is in an online mode. And you can learn a lot if you are a beginner. If you're someone like me who likes to go in depth of everything and who likes to take these semester-long courses and who likes to make notes and everything, then I love MIT OpenCourseWare for this one. There are many courses there. I've done linear algebra and multivariable calculus. These are, I'm warning you, these are not like online resources that you study, the 3-minute videos and then you can jump onto the quizzes. These are not like that. These are actual semester courses by the MIT. So you would want to sit down and make notes for this one, but it will give you the best wholesome knowledge for the entire subject. The one that I particularly like is Matrix Methods in Data Analysis, Signal Processing in Machine Learning by MIT OpenCourseWare. This is because there are a lot of lessons on the applications of matrix methods, that is linear algebra and multivariable calculus both, with these with applications in these fields, right? So you would get a very good idea, and don't worry if you're a beginner, because it has a lot of introduction part too, and you would get a very good idea of what the subject actually entails and how is it going to be applied to your field, which is your motive in the end. One YouTube channel that I really suggest is called 3 Blue 1 Brown by Grant Sanderson. This is an amazing YouTube channel if you are into, visual learning. You will find all the hot topics there. There are neural networks, there are Fourier series, but it is mostly about mathematics. You will really like the topic, the videos here, because a single topic is explained by 3 or 4 different perspectives. So you will really get an insight into what the topic has to offer you. Some books that I really like, if you are more into reading books, are Introduction to Linear Algebra by Gilbert Strang. Now, this one, I guess, is the holy grail of linear algebra everywhere for undergrad education, I guess. And this one is very introductory. It is very interactive, and it is very comprehensive at the same time. So you would really enjoy it. There is Multivariable Calculus by James Stewart, and there is a course in probability by Sheldon Ross. Now, all of these are, there are my personal vouchers for starting your mathematics journey. Now, in the end, a very little sneak peek of the flip side of the entire topic, like how is AI, how is artificial intelligence being used in solving mathematics problems? So the figures that you see are actually a part of my own research. I researched with my team, I researched on learning partial differential equations from data using AI, using neural networks. So I'll just quickly explain the figures if they're new to you. The leftmost figure is the one soliton solution of Burger's equation that you see in physics. Then the middle figure is actually after adding 50% noise. So you're adding 50% error to the data that you have simulated. So that is after adding 50% noise. And the right-hand side figure is after learning the partial differential equation back from the data using neural networks. So I guess they look pretty similar and pretty accurate. So yeah, that's that. AI is being used in solving also PDEs, partial differential equations, and they're also being used in learning PDEs, as in they're trying to fit PDEs on data, on huge data, experimental data, or simulated data. Now, I've also added a link to a very interesting article by Facebook Research a couple of months back, I guess. They have developed a model that actually solves advanced mathematical equations using AI. And so they're not doing it through the neural networks part. They're actually doing it through um, NLP, through natural language processing. So they're trying to learn they're trying to detect the equation as a language, as a sequential syntax, and they're trying to then solve it. So it's very interesting if you want to go through it. Yeah, so that's that. And this is something that Bloomberg Business Week published a long time back, I guess. And they said that there has never been a better time to be a mathematician. So if in some way I have, convinced you to start your math journey, to actually take up your math books and start practicing, then I'd love to connect with you, and you can find the links here, or you can just type Kashvi Srivastava and you will find me. So yeah, that's that. Thank you so much. Thank you so much for being here. I think I should stop sharing. Yeah. Thank you so much.
Okay. So thank you, Kashvi, for those amazing insights that you shared. And you just didn't tell about the different topics, but you even gave us the resources. So that was really good. And if anyone has any questions, so they can post it in the live chat.
So if I'm audible to the audience, I think I lost Anushka. Yeah, she's back.
Yeah, so you can just post your doubts in the
Anushka, your voice is breaking. So
okay, so Kashvi, like over. Okay. Is it fine now?
Yeah.
So people have actually praised you, and like they have really all the resources and all that you have shared with them, and they really like the session. There's a question that I can see. I'll just post it on the main screen.
Yeah, so should I read it out? If I'm audible to the audience, I think I can continue, because I think there is some network issues with the host today. So yeah, Mihir Alawat asked, you talked about black box optimization. How is black box optimization related to black box machine learning models? So hi, can I just continue answering the question? Anushka,
okay,
you're not.
so there's another question that
I can hear you. Yeah, I can hear you. Don't worry.
I don't know.
I think I'll go back to the last question first because I was not able to answer that. I guess I can answer this one, and we'll move back to the last question after that. So Dheeraj Sona when asks, how can a physician get the maths knowledge to such extent if he's interested in AI? To this, I would say that AI and machine learning and all of this are pretty fairly new research fields, and whatever you are trying to do, if you're trying to develop if you're trying to develop concepts in these fields, then it would be counted as research, right? And for whatever research that you're trying to do in the field, you will need a sound math knowledge before actually coming to conclusions, and even for backing whatever research that you have done, right? So if you're a physician, I would say, as far as I know, even physics requires a lot of math background, and most of it depends on a lot of pure math and a lot of calculus, I would say. So if you're interested in AI and want to start using physics and AI together, there are a lot of resources which can get your hand on maths. As I shared, some of the books that I shared are very crude. They're very basic and very like introductory. Even if I was to start my math journey from there, I would have totally gone with it, because they are made for someone who's trying to learn it, right? If you're wanting to learn AI and with a perspective of actually delving deeper into it, of actually developing things which are useful for different fields, or even your field, even physics, because I've seen a lot of research going on in the intersection of physics and AI, like Physics and Neural Networks by Mazia Raisi, I guess, if that's something that you're interested in, or using Hamiltonian functions in neural networks. So all of this research requires a lot of math, and if you're trying to gain that amount of that, sense of knowledge of math, there are a lot of resources. There are very introductory resources. I'm sure if you're a physician, you must have heard of the book, The Physics Lectures by Feynman. So that is something that is considered to be a pioneer in physics, right? So the books that I'm talking about, like by Gilbert Strang, by by Sheldon Ross, these are all our pioneers, and they're written in a certain way to actually engage your curiosity in maths. So if you're really interested in it, there are a lot of resources. There are a lot of very good books by very respected pioneers in the field, which can get you through. Yeah. I think I wanted to go back to the first question because I was not able to answer that, or we can, jump to any other question that you want.
Yeah. Yeah. I'll just take you to back to the first question that we had. Just a second. Okay, so this was related to black box optimization.
Yeah, sure. I can speak on that. So black box, I guess, is the same term is being used in two different contexts here. Like in black box machine learning models, what they mean by black box is actually that you don't understand the working of the model itself. you're not understanding, you're not clear with what the model is doing and how is it producing a certain result if it is getting a certain amount of input. Now, black box optimization is more or less working on the same phenomenon, but it is used for functions which are not analytically expressed. So you do not know the exact expression of the functions. You do not know if there are derivatives of the functions, or if they are present, or if they do not exist. Like, you need derivatives for optimization, right? You take the derivative and then you put equal to 0, and then you take out the critical points. So yeah, so in black box optimization, what you are assuming is that you do not know how the function actually is, and you are just assuming whether or not derivatives are present or not. So there are many methods. There are like two types of methods: model based and direct search. And I can go in detail, but for a brief introduction, I would say that if you're assuming that your function might have some derivatives, and it is just that you are not able to attain those, or these are not experimentally available, then you can use model-based methods in which you approximate your function through a different function, and then you are using the approximated function to calculate the derivatives and everything to actually optimize the original function. And in the other type of methods, you are just assuming that there are no derivatives at all. The derivatives do not exist. That means that your function is not smooth. So that means that you can use a certain initial point, and then you can find the points in the neighborhood of that point, which will comply with your result. So that is a brief introduction. If you want to know more about black box optimization, then you can always search the resources on black box and derivative free optimization. Yeah.
So there aren't any more questions in the chat box. So that's it. And thank you so much, Kashvi, for your time and like for sharing all these insights with us. It was really good to host you and to hear to you. And to all the ones who are watching this live session, thank you so much for joining in. And we do have sessions lined up tomorrow also, and in the further weeks also. So we hope to see you all there.
Thank you so much for having me again. Thank you so much.
All right, so we're just ending the broadcast, and thank you.
Thank you.
Yeah. Is it over?
It still shows live to me, so I don't think.
Broadcast over. No. Just a second.
I guess I have another question. So if you want to continue that.
Just a second. Okay. Well, actually, I'm not able to see that question. I can just see two questions.
This is, yeah, it just came in at 4:47 p.m. By Mehal Patni. If you're still able to see it, or I can just call out the question and then answer.
So you can just address that. I just don't